तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Today we shall consider about normal forms. Already we considered a little bit about what is meant by a disjunctive normal form and conjunctive normal form, and conjunctive normal form we took as class form and we used it in resolution principle. But again we shall go through those definitions and also what is meant by principal disjunctive normal form and principal conjunctive normal form, and in the first order logic what is meant by Prenex normal form. So, let us recall some definitions which we learnt earlier. A product of the variables and their negations in a formula is called an elementary product. For example, something like P and Q and not R, something like this is called an elementary product. Similarly, a sum of the variables and their negations is called an elementary sum. For example, something like P or not P or Q or not R, something like this is called an elementary sum. Now, you can see that a necessary and sufficient condition for an elementary product to be identically false is that it contain at least one pair of factors in which one is the negation of the other. Suppose I have an elementary product like this, and if it is like this, say, if it contains one pair of variables or one pair of literals where one is the negation of the other, you have Q and not Q, then this becomes identically false, because you know that Q and not Q is 0, that is false, and something and 0 is 0. So, an elementary product is identically false if it contains two literals where one is the negation of the other. And the other way around, a necessary and sufficient condition for an elementary sum to be identically true is it contains at least one pair of factors in which one is the negation of the other. So, suppose I have something like this, P or not P, Q or not R, something like that, then you have one literal and the negation of the variable in another literal. So, you have one variable and also the negation of that. This we know that is a tautology. P or not P is 1. So, 1 or something, that will be 1. Now, any formula involving the connectives using propositional variables is called a WFF, or well formed formula of propositional logic. Now, any well formed formula of propositional logic you can bring into conjunctive normal form or disjunctive normal form. First, let us define what is meant by that. First let us take disjunctive normal forms. A formula, that is a well formed formula, which is equivalent to a given formula and which contains a sum of elementary products is called a disjunctive normal form of the given formula. So, it should be of this form, something like, no, it should be the sum of elementary products. Okay. So, a sum of elementary products is called a disjunctive normal form. It will be something like this, or again something. Now, any well formed formula we can bring into disjunctive normal form. Let us take some examples. First, let us take this. We want to bring this well formed formula into disjunctive normal form. How do you go about doing that? First of all, you can convert implication into not. So, this will become not of P or not of Q. P implies Q, you can write as not P or Q. So, this can be written as not of this or P is equivalent to not Q. Now, P is equivalent to not Q, you can write as, suppose you have P is equivalent to Q, this is equivalent to saying P and Q are not P and not Q. This we have either both of them must be true or both of them must be false. This we know. So, using this rule here, you will get this portion is as it is. This you can write as P and not Q, P and not Q, or not P and not P and not of not Q. So, using De Morgan's laws, this will become P and Q, because this will become not of P and not of Q. Maybe I will write that step also, not of P and not of Q, using De Morgan's laws, and R, and this will be P and not Q, and this will be, there should be a bracket here also, not P and Q. So, this is equivalent to saying P and Q or P and not Q or not P and Q. So, this is an elementary product, this is an elementary product, and this is an elementary product, and you have a sum of elementary products. So, this is a disjunctive normal form. Let us take one more example. Let us convert this into again disjunctive normal form. How do you go about doing this? P implies Q and R. So, implication you can convert into not P or Q. So, this will be not P or Q and R, and this one again you can write like this, not of P or not Q and not R. So, this again you can write as not P or Q and R and P or not Q and not R. Now, you can use distributive laws. We can write this as not P R Q and R and P are not P R Q and R and not Q and not R. Again, here you can use distributive laws, and this will be not P and P are Q and R and P are, here again you can use distributive laws, and this will become not P and not Q and not R are Q and R and not Q and not R. We can remove unnecessary parentheses and write it in the proper form. So, here it is an elementary product, here again elementary product. So, if you rewrite this, it will become not P and P or Q and R and P or this one will be not P and not Q and not R, and this will be Q and R and not Q and not R. So, this is the disjunctive form, normal form. Again, I want to mention that disjunctive normal form or conjunctive normal form is not unique. For example, this you know that Q, you have Q and not Q. So, this whole term is 0. So, it can be omitted. So, it is not unique, but any formula you can bring it to the disjunction of elementary products. Next, we shall consider conjunctive normal form or CNF, that is the one we used earlier. What is a conjunctive normal form? A formula which is equivalent to a given formula and which consists of a product of elementary sum is called a conjunctive normal form of the given formula. So, it will be like this, it will be something like P R Q and something R R. This is called conjunctive normal form. It is the product of elementary sum. Each one is an elementary sum, and you have AND here, product of elementary sums. Again, any well formed formula of the propositional logic, you can bring it to conjunctive normal form. Let us take one more example here. So, this is the formula and we want to bring it to conjunctive normal form. So, this you can write as not of P or not of Q using rule for implication. P implies Q can be written as not P or Q. So, not of this, or this one you can write as P implies not Q and not P, P implies Q and Q implies P. So, not Q implies using De Morgan's laws, this will become P and Q are not P or not Q and not of Q or P. Here again I am using the rule not P implies Q is not P or Q, and same rule here. So, what will you get? You will get P and Q are not P or not Q, and this will become not of Q is Q. So, you will get P or Q. You can use distributive laws now. So, this will become P or not P or not Q and P or Q and Q not P or not Q and P or Q. So, if you expand this using distributive laws, you will get P or not P or not Q and P or P or Q, and this one will become and okay, I have omitted, there is a R here which I have. Q or not P or not Q and Q or P or Q. So, this is an elementary sum, 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 and you have the product of elementary sums. This is a conjunctive normal form. Now, you can see that because you have P or not P, this will reduce to 1, and because you have Q or not Q, this will reduce to 1, and this will reduce to P or Q, and because P or P is P and Q or Q is Q. So, ultimately the whole thing will reduce to P or Q. If you simplify, if you want to simplify, this will reduce to this, but we are not at present interested in that. This is the conjunctive normal form. So, any well formed formula of the propositional logic can be brought into either disjunctive normal form or conjunctive normal form. Now, we will consider principal disjunctive normal forms. Let us take two propositional variables P and Q. Now, consider the terms P and Q, or P and not Q, or not P and Q, and or not P and not Q. They are called min terms. There are 4 min terms here. P and Q is a min term, P and not Q is a min term, not P and Q is a min term, not P and not Q is a min term. In a min term, every variable will be present only once, either in the negated form or in the non-negated form. So, if you have two variables, it is the conjunction of two literals they can be negated or non-negated. Now, what is a principal disjunctive normal form? For a given formula, an equivalent formula consisting of disjunction of minterms is known as its principal disjunctive normal form. Such a normal form is also called the sum of products canonical form. So, you should have disjunction of minterms. Earlier we had disjunction of elementary products. Here we have disjunction of minterms. So, let us see how to convert a given formula into principal disjunctive normal form. Let us take some example. Now, consider this example: P R, not P implies not Q implies R. This you can write as P R not P implies. This one, by changing into the form, you can write it as not of Q is Q R R. So, this you can write as P R, again not of P, P R Q R R. So, this will become P R P R Q R R, which is nothing but P R Q R R. Now, this is a sum of elementary products, but each one should be a minterm. This is not a minterm. So, we have to convert this into a minterm, for which you have to add the variables Q and R. Now, you know that P you can write like this: P is P and Q R not Q, because Q R not Q is 1 and P and 1 is P. So, you can write like this, and R R not R, and then if you expand using distributive laws, this will become P and Q and R, R, P and Q and not R, R, P and not Q and R, R, P and not Q and not R. So, you will see that each is a minterm, this is a minterm, this is a minterm, this is a minterm, this is a minterm. So, P is equivalent to these 4 minterms, sum of the 4 minterms. Similarly, you can write for Q also. Q will be equal to P and Q and R, R not P and Q and R, R, P and Q and not R, R, not P and Q and not R. So, you have to provide the missing variables. Here you have only Q, P and R are missing. So, you have to provide them in all possibilities. So, you have P R, not P R, P not R, not P not R, like that you have to provide. Similarly, R also you can write. Ultimately, the whole formula will be equivalent to, you can omit repetition, P and Q and R is there, here also it is there. The whole formula will become P and Q and R, R, P and not Q and R, R, P and Q and not R, R, P and not Q and not R, R, not P and Q and not R, not P and Q and R, R, not P and not Q and R. So, out of the 8 possibilities of combining them, if you each variable should be present in the min term either in the negated or in the non-negated form. So, with 3 variables you can possibly have 8 min terms, and in this formula out of the 8, 7 are present. So, this is the way you convert a given well formed formula into principal disjunctive normal form. This is also called sum of products. Each is a product and you have the sum of them. Now, there is a way of writing this. Usually you write not P or not Q or not or S 0 0 0, not representing 0. For example, P and Q and R S 1 1 1, P and not Q and R, I am sorry, this is AND, P not Q and R, this you can write as 1 0 1, like that. So, the 8 possible min terms you can represent by binary numbers from 0 to 7. So, in this case what will this represent? This will represent 1 1 1, that is 7, and this will represent 1 0 1, that is 5, and this will represent 1 1 0, that is 6, and this will represent 1 0 0, that is 4, and this will represent 0 1 0, that is 2, and this will represent 0 1 1, that is 3, and this will represent 0 0 1, that is 1. So, if you allow the min terms to be represented from 0 to 7 in this case, in general if you have n variables, the min terms you can represent by integers from 0 to 2 power n minus 1. So, if you do that, you represent the principal disjunctive normal form as sigma. For example, this one you can represent as sigma 1 2 3 4 5 6 7. With 2 variables, suppose I have 2 min terms P and Q, not P and not Q, and a principal disjunctive normal form like this. How will you represent this? There are only 2 variables, they can be represented from 0 to 3, and this will represent 3, 1 1, that is 3, and this will represent 0 0, that is 0. So, this whole expression you can write as sigma 0 comma 3. Next, we shall consider principal conjunctive normal forms. We shall first define what is meant by a max term. For a given number of variables, the max term consists of disjunctions in which each variable or its negation, but not both, appears only once. So, suppose you are having variables P and Q. With P and Q, what will be the max terms? P R Q, not P R Q, P R not Q, and not P R not Q. These are called max terms. They are disjunction of literals where each variable is present in the negated or non-negated form, but not in both forms. So, any formula you can bring into principal conjunctive normal form. What is principal conjunctive normal form? For a given formula, an equivalent formula consisting of conjunctions of max terms only is known as principal conjunctive normal form, and this is also called product of sums canonical form, and any formula can be brought into principal conjunctive normal form. Let us see how we can do that. The earlier example which we considered, this one reduced to this, then we added extra variables to make it to principal disjunctive normal form. Now look at this, this is a max term with 3 variables, this is a max term. So the whole thing reduces to just one max term in this example. Let us consider one more example, Q implies P and not P and Q. This you can write as not Q and not P and Q. So this is not Q or P, this is a max term, and not P and Q. Now you have to convert them into max terms. So not P you can write as not P or Q and not Q. This is 0. So not P or 0 is not P, and this one using distributive laws will become not P or Q and not P or not Q. Similarly, Q can be written as P and not P or Q. You have to provide the missing variable like this, that is equal to, using distributive laws, P or Q and not P or Q. So the whole formula reduces to not Q or P, that I will write as P or not Q using commutative laws, not P. This term becomes like this, not P, P or not Q, and instead of not P you have to write these two terms, not P or Q and not P or not Q, and instead of Q you have to write these two terms, P or Q and not P or Q. Now you can see that not P or Q is repeated twice. It is not necessary to write twice. So probably you can remove this. This is repeated. So you have the conjunction of max terms. Each is a max term, and you have the conjunction of max term. This is the elementary. This is the principal conjunctive normal form. Now the notation for that is, so a principal conjunctive normal form is a product of max terms. So with 2 variables I have the max terms like P, not P or not Q, not P or Q, P or not Q, P or Q, and this you can represent in binary like 0 0, 0 1, 1 0, 1 1, representing the numbers from 0 to 3. So if you look at the last one which we consider, all the 4 terms are present here, all the 4 max terms are present. So this can be represented as product 0, 1, 2, 3. So this is the notation used. Now with 3 variables again you can have the max term represented by 0 to 7, and if you look at this one, this represents the max term 1 1 1 or 7. So the whole formula can be represented by pi 7. Suppose I have P or Q or not R with 3 variables and not P or Q or R and not P or not R, not Q or R. Suppose a formula consists of these three max terms. This will represent 0 0 sorry 1 1 0, and this will represent 0 1 1, and this will represent 0 0 1. So, the whole thing can be written as pi of 1 comma 3 comma 6. The formula you can write as pi 1 comma 3 comma 6. So, this is another notation for writing the principal conjunctive normal form as we consider for principal disjunctive normal forms. Next, we have to consider Prenex normal form. So far, we have considered only propositional logic. We did not use quantifiers at all. Now, if you use quantifiers, how will you write it in a normal form? What is the normal form for first order logic? For first order logic, the normal form is called Prenex normal form, and the definition is like this. A formula f in the first order logic is said to be in a Prenex normal form if and only if the formula f is of the form q1 x1 q2 xn m, where x1 x2 xn are the individual variables. So, every qi xi is of the form for all of xi or there exists xi. q1 represents a quantifier for x1, q2 represents a quantifier for x2 and so on. It can be the universal quantifier for all or the existential quantifier there exists. And the rest of the formula is given in M, and M is a formula containing no quantifiers. Now, the q1, x1, q2, x2 etc., this is called the prefix of the formula, and M is called the matrix of the formula. Now, any well formed formula of first order logic, you can bring it to Prenex normal form. Let us see how to go about that. The steps you have to go through are given like this. If you want to bring any well formed formula of the first order logic, how to transform into Prenex normal form? First step will be use the laws, that is, if f is equivalent to g, you have to replace it by f implies g and g implies f, and if you have f implies g, you have to replace it by not f or g. Then by this you will be eliminating the logical connective, equivalence and implication. The second step will be repeatedly use not of f is equal to f, and De Morgan's laws, not of f or g is not of f and not of g, and not of f and g is not of f or not of g. And also the laws, not of for all of x f of x, by bringing the not inside, for all will change to there exists. These things we have learnt earlier. So, this is equivalent to saying there exists x not of f of x. So, you are bringing the not inside. Similarly, here if you have not there exists x f of x, bring the not inside and you will get for all of x not of f of x. So, the second step is to bring the negation signs immediately before the atoms. The third step is rename bound variables if necessary. We shall see what it is by taking some examples. And step 4 will be make use of the laws. Now, if you have q of x, f of x or g, where g does not contain x, you can write it like this. Similarly, if you have q of x, f of x and g, where g does not contain x, you can write it like this. And for all distributes over end, so this one can be replaced by taking for all of x out and writing this way. This for all of x f of x, and for all of x h of x you can write as for all of x f of x and h of x. and there exists x distributes over R. So, in a similar manner, if you have there exists x f of x or there exists x h of x, you can take out the there exists x and write it as there exists x f of x or h of x. But if you have for all and R, you cannot use that, and similarly there exists will not distribute over, and this you have to remember. Now, if you have q1x f of x or q2x h of x, then how can you bring out the quantifiers? Q1, Q2 can be for all or there exists. How can you take them out? Now, this x or this quantifier is binding this portion, and this quantifier is binding this portion. So, the best thing for us will be to rename one of the variables. So, keep x here, and instead of x you write it as z. In that case, this will not have x and this will not have z. So, you can take the quantifiers out. This is renaming of variables. So, keep it as it is, and this one you replace by z, rename as z, and then take out the quantifiers. So, this you will get as q1x, q2x, f of x or h of z. You are renaming the variable here. This is using or, this is using and. Here again you have the same thing. If you have q3x and q4x, this is binding this and this is binding this. So, it is better to rename this variable as z, and so by taking out the quantifiers you will get this. That is to move the quantifiers to the left of the entire formula to obtain Prenex normal form. Let us consider one or two examples. So, let us consider some examples to see how to convert a well formed formula of first order logic into Prenex normal form. We have to bring all the quantifiers to the front, and the rest of the formula should be after the quantifiers. The first one is called the prefix and the latter one is called the matrix of the formula. Now, take this example. For all of x, p of x implies there exists x q of x, and we have seen what are the steps we have to use in converting a formula of the well formed formula of the first order logic to Prenex normal form. First, we have to replace equivalence and implication. So, let us try to replace this implication. This you can write as not for all of x p of x or there exists x q of x. So, this given formula is equivalent to this. This is we are using the rule p implies q is equivalent to not p or q. Now, the next step will be to bring the not nearer to the atom. P of x and q of x, they are the atoms. So, how will you bring the not inside? When you bring for all of x will become there exists x. So, you have there exists x not of p of x or there exists x q of x. We know that for all distributes over n and there exists distributes over R. So, we can use distributive law in the reverse and take the there exists out. So, you can take out there exists x and write it as not of p of x or q of x. This is in Prenex normal form. This is the prefix and this is the matrix. Let us take one more example. This has 4 variables. This is the well formed formula involving 4 individual variables x, y, z, u. For all of x, for all of y, there exists z p of x z and p of y z implies there exists u q of x, y, u. Here P is a predicate variable with 2 variables and Q is a predicate variable with 3 variables. It is a ternary predicate. The scope of x for all of x and for all of y will be the whole thing. The scope of there exists z is this portion. The scope of there exists u is this portion. So, we must be very careful about the scope of each quantifier. Now, fortunately in this example, the 2 quantifiers for all x and for all of y are outside the rest of the portion. We need not have to do anything about them. Only the remaining thing we have to change. So, this can be written in this form for all of y, and this one again the first step is to replace implication by using P implies Q is equivalent to not P R Q. So, this can be written in the form not there exists z P of x comma z and P of y comma z, or there exists u Q of x y u. Now, the for all of x for all of y remains as it is. The second step will be to bring the not inside. So, in that case you will get there exists will become for all. So, for all of z not of P of x z and P of y z. Okay. For all z is the whole thing, this is, and there exists u Q of x y u. Now, for all of x, for all of y, this you can write as for all of z, use De Morgan's laws, this will become not of P of x comma z or not of P of y comma z, and the scope of z is this portion, or there exists u Q x y u. Now, you can see that the scope of z is this portion and z is not occurring in this portion at all. And similarly, u there exists u, the scope is this, and u is not appearing in this portion. That way this portion is free of u and this portion is free of z. So, using for all z here is not going to affect it in any way because this does not contain z, and using there exists here, there exists u here is not going to affect because this portion does not contain u at all. And for all of x, for all of y, the scope is the whole thing and they are already outside. So, we need not bother about that. So, without affecting the formula, we can take out for all of z and there exists u outside. This is possible because this does not contain z and this does not contain u. Supposing it contains something, we have to rename the variables and things like that. So, in this particular example, there is no necessity for renaming of variables. So, what you get is for all of x, for all of y, for all of z, there exists u, then you get not of P of x comma z or not of P y comma z or Q of x y u. So, we have brought the given formula into Prenex normal form. This is the prefix which contains all the quantifiers, and this is the matrix portion which does not contain any quantifiers. Like that we can bring any formula of first order logic into Prenex normal form. Propositional logic also you can look at as Boolean algebra, which has got application to switching circuits. I am not going into detail of these circuits, but you must have heard about AND gate, OR gate and so on. An AND gate is represented like this. It has got two inputs and the output is P and Q. P and Q can be 0 or 1, and the output will be 1 when P and Q are both 1, otherwise it will be 0. This is known as the AND gate in switching circuits. An OR gate, this is AND, an OR gate is represented like this. There will be two inputs P and Q, and the output will be P or Q. It will be 0 when both P and Q are 0. When one of or both of P and Q are 1, it will be 1. It represents the AND connective in the propositional logic. Okay. The NOT gate in switching circuits is represented by this. There is only one input and the output represents NOT P, and this is called the NOT gate. In switching circuits, we also have two more gates known as the NAND gate and the NOR gate. NAND, which is actually not AND, complementary to AND, and the truth table for that will be like this: PQ. The null operator is usually denoted like this: Pierce arrow, when this is 0, this is 0, this is 0, 1, you have to consider the four possibilities: 1 0, 1 1. In the case of AND of P and Q will be 1 in this case. So, not AND will be, this is 0. In the other cases it will be 1. So, it is complementary to the AND table. P and Q will be like this. P and Q will be, so it is complementary to that. This is represented by a gate of this form, or we also have another gate, NOR, which represents not OR. The truth table for that will be like this: P Q. This is sometimes represented by this notation. Again we have possibilities 0 0, 0 1, 1 0, 1 1. What will be the table for P R Q? P R Q will be 0 in this case, in the other three cases it will be 1. So, it is not of R, so it will be 1 0 0 0. The truth table for NOR gate is given by this. It is represented by a diagram like this with two inputs P Q, P Q. Now, any Boolean function can be represented by a Carnot map, and you have it is you can represent it as a canonical sum of products or disjunction of minterms. For example, involving two variables P or Q or R, if you represent it, I again do not want to go into the details what is meant by a Carnot map and all that. Those who are familiar can connect it up with this. These, suppose I have three variables P, Q and R. This is P, this is say Q and R. Then 0 0 0 is this, 0 0 1 is this. Better use P, Q and R here. So, 0 0 will be this, 0 0 1 will be like this, 0 0 1 0, 3 4 5 6 7 cells can be represented like this. P will be represented by this, Q will be represented by this, and R represented by this, which includes all the 7 cells, and this will be written in the form sigma of 1 comma 2 comma 3 4 5 6 7. This we have already seen. So, this is to show the connection between Boolean algebra or propositional logic and Boolean algebra and switching circuits. We already know what is meant by AND, OR, NOT. Two more gates are there in switching circuits, NOR and NAND, and any Boolean function can be represented like this as a principal disjunctive normal form.